Hello students, welcome to Inside Physics. I am Srinivas. Today we will discuss about ray optics. Ray optics is a lesson on light in which the light is considered as a ray. Okay, whenever a light is considered a ray, we will study the reflection of light, refraction of light. So, as considering the light as a ray, we will study the properties of its reflection and refraction through plane curved surfaces and curved mirrors and lenses. Okay. Here in this lesson, we only consider curved mirrors and lenses. Okay. So here ray optics. I will briefly introduce you the properties of light before going to the study of ray optics. See, light is an electromagnetic wave considered as a electromagnetic wave in which the electric and magnetic fields are mutually perpendicular considering their planes of propagation. So, in that way, the electromagnetic wave propagates something like, see, when an electric field in the light is propagating in this way, so the magnetic field will be propagating perpendicular to this plane. So, this is electric field. So, in this way, the perpendicular to the electric field, there is magnetic field propagating. So, simultaneously, the electric and magnetic fields pushing through each other, the propagation of light happens and the light wave moves further. Okay. See, the electromagnetic spectrum, in the electromagnetic spectrum, the visible spectrum, the visible spectrum is between 400 nanometers to 750 nanometers. So, in this wavelength, in the limit of this wavelength only, we can see the light. Beyond 750 nanometers or below 400 nanometers, there are radiations, but we cannot see them. So, in this way, our retina is sensitized to see this radiation between 400 nanometers to 750 nanometers. So, in this way, we interpret the world by seeing the radiation coming around us and the radiation going through our eye and falling on the retina. It actually creates some images. Okay. So, in this way, we see the world with the help of the light reflecting from other objects. Okay. So, with intuition, actually, we can say, and with so many help of the experiments done previously, we can say that the light can move with enormous speed, high speed, and it moves in a straight line. Okay. So, the experimental observations of light given a value of 2.9978 into 10 to the power of 8 meters per second, the speed of the light. Okay. So, here if you consider for our practical purposes or when we are considering the velocity of light in any problems, we will generally round it off and we will consider it as 3 into 10 to the power of 8 meters per second. So here the velocity of light by looking at this value is very high, and this is the maximum attainable speed in the universe. The velocity of light is the maximum attainable speed in the universe. Okay. So here next one, if you observe the second property of light, it is actually considered to be moving in a straight line. moving in a straight line if the light ray is passing from A to B. But when we consider light as a wave, see, the straight line motion is not at all practically possible when we consider the light ray as a wave. So how can we justify that the path of the light ray is a straight line? So whenever we compare the wavelength of light with the obstacles, suppose a light ray is moving in this direction and there is an obstacle here which is in the path of the light ray. So when we compare the wavelength of light with the size of the object, the wavelength of light is so small. Even when we consider if the object is around 1 centimeters or 2 centimeters, so when the wavelength is compared to the size of the object, compared to size of the object, wavelength of light is very small. So obviously the wave will be passing through is in a straight line without getting disturbed by the object because the wavelength is so small. In this way, we consider the light is moving in a straight line. So if we consider the wavelength is moving in a straight line, the path of the light ray is considered as a ray. The path of the light ray in a straight line is considered as a ray. So here if a single ray is constituting the light ray, and if you consider a bunch of rays, suppose a number of rays, a bunch of rays together is called a beam of light. Is called a beam of light. So in this way we will see what exactly the light picture is and how we consider light as a ray in this lesson. So after this we will see what is corpuscular theory. Corpuscular theory proposed by Newton. He proposed a theory for light. We know Newton is a great scientist. He has done so many experiments in mechanics, gravitation, mathematics. So with his great reputation, he proposed a theory called corpuscular theory, in which he said that light is moving in a small particles called corpuscles. Small particles called corpuscles. So these corpuscles, he actually gives some characteristics of corpuscles, like they are one, massless and elastic. Massless elastic particles, something like a particle with these two properties called corpuscles. So he said that light is propagating in the form of corpuscles. He tried to explain the behavior of phenomenons of reflection and refraction with the help of corpuscle theory. So, as we know, Newton is a great scientist in mechanics. He tried to explain the reflection property of light on the help of mechanics. See, when the light is considered as light is considered to be moving in the form of corpuscles. He said that whenever there is a surface and if a ball is dropped on this surface, it will be bouncing back, okay, losing a small amount of energy. If it is a perfectly elastic surface, so the bouncing back and the height, after bouncing the height reaches by this ball is same as the dropped height if it is a perfectly elastic collision between the surface and the ball. Here the vertical momentum is completely reflected back. the vertical momentum is completely conserved, and the vertical momentum is the cause for the ball to hit the surface and bounce back. So in the here there is no consideration of horizontal momentum. In this way, he said that whenever some corpuscles, the light corpuscles are incidenting on a surface, like this, he said that if it is a polished surface, and these corpuscles will be reflecting back just like the a ball is reflecting from a hard surface. So here, after that, see, this reflection phenomenon is actually practically not viable as said by the Newton. So it is unable to explain the laws of reflection, the corpuscular theory. And after that, he tried to explain the refraction process based on this same theory. Okay, so refraction is a process of bending of light whenever it is touches an interface between two mediums. If this is an interface border between two mediums, see, whenever there is a light ray participating, touching this incident interface, incidenting here. Okay, so refraction on the basis of corpuscular theory, he said that whenever a light ray is passing from rarer medium to denser medium, suppose air to water from air to water, he said the velocity of speed of light will increase in the denser medium. If it is water or glass, any denser medium, the speed of the light will be increasing in that medium. In that way, he said that the refraction will take place. But actually, in practical observations, the speed of light will be the less than air or vacuum. So the speed of light is decreasing whenever it is moving from a rarer medium to denser medium. Okay. So, and if whenever there is some refraction, there is also some reflection process. So the light ray will be partially reflected and partially refracted in some cases. So if you look at some water pool, and when you are observing your face on the surface of a water pond or pool, you can see the image of your face, and you can see the underground floor of the pond also. So that means the light ray is partially reflecting back, and, and the light ray is refracting through the water, and it touching the ground surface also. From there it is reflecting back. So this phenomena Newton could not explain on his corpuscular theory. The first question arised is, see, he said that some corpuscles will be reflected back, and some corpuscles will be passing through the interface of the medium, getting into the second medium. But when a question arises, what is the distinction? What kind of corpuscles will be reflecting back, and what kind of corpuscles will be passing through the second medium? But he could not distinguish the corpuscles, how the reflection and refraction taking place on what principle. So in this way, the corpuscular theory could not explain the reflection and refraction process. If we consider the light ray as a wave, we can successfully explain the refraction process here. See, whenever light ray is incident on an interface between two mediums, see, the light wave will be divided into two parts, and the intensity will also be divided into two parts. So the light wave is, if it is considered as a wave and incidenting on an interface, so it will be partially refracted and partially reflected back. The light ray will be splitted into two waves. Okay, So by wave theory, we can successfully explain the reflection and refraction process. Now we move to what is actually reflection. Reflection, reflection at spherical mirrors. Here in this lesson, we don't consider any plane surfaces, even though the reflection happens at plane and curved surfaces. Okay, we only consider here the spherical, that means curved mirrors, mirror and lenses. So reflection is a process when the light ray is incident on a plane or spherical mirror. The light will be reflected back, and we have some principles of reflection. Okay, what is the first principle means? Whenever there is a light ray incidenting at the interface of a two mediums, if we consider this as incident ray, this is the incident ray, and I is the angle of incidence. So the reflected ray will be also having the same angle as of the eye. So the incident ray and the reflected ray are having the same angle of incidence and reflection. So how we measure the angle of incidence and angle of reflection? If we draw a normal, this is a normal to the interface between medium 1 and medium 2. So this normal to the interface, this is the incident light ray. The angle between the normal and the incident light ray is called angle of incidence. I is angle of incidence. Okay. And in the same way, the reflected ray, by reflecting it from this point, the angle made by the reflected ray with the normal is called angle of reflection. Angle of reflection. Okay. So when it is, if you consider the second principle, what is the second principle means? The incident angle and the normal to the interface and the reflecting ray, the incident ray, the normal and the reflecting ray, all the three will be in the same plane. Okay, the same plane means if this board is considered as a plane, the incident ray, normal and the reflected ray are exactly in the same plane. In this way, the second condition is the all the three incident ray, normal and the reflected ray lie in the same plane. These are the two principles of reflections that we can observe in the process of reflection. Okay, if it is a spherical surface, if it is a spherical mirror, suppose, okay, see the tangent drawn here. If you take any point on the mirror and a tangent is drawn to the mirror, see the line connecting from the center of curvature to the center of curvature to the incident point. So this radius of curvature is perpendicular to the tangent drawn at the point of incidence. Okay, so any ray coming to from the center of curvature of the spherical mirror, so will be reflected back and passing through the center of curvature, because this is exactly perpendicular to the point, the to the spherical surface at the point of incidence. So in this way, these laws of reflection are applied in the process of studying reflection at spherical mirrors. Now we see what is before going to the actual derivations of formulas for focal length and the derivation of mirror formula, we need to understand what is sign convention. Sign convention. Sign convention means the positive or negative kind of a direction according to the distance. So here the in the sign convention we just consider a spherical mirror. Okay, this is the principal axis. This is the principal axis. A line connecting from the center of curvature to the pole of the mirror is called principal axis. Okay, so if we want to measure any kind of distances like focal length, radius of curvature, and object distance and image distance, these distances are actually measured from the pole. From the pole. So we know that the distances are measured from the pole. And what is the direction and what is the sign that we have to give to the value of distances means that depends that sign value plus or minus will depend on the direction of the incidenting light. If it is the direction of the light ray incident at this point and we consider the light direction is in this direction, and here the measurement of focal length, or suppose if this is the focus, this is the focus and this is focal length, this is called radius of curvature, or this is center of curvature, this is focus, this one is focal length. So here if you consider the focal length, it will be measured from pole P to F. If it is, if you want to measure the radius of curvature, if it is from pole P to C, center of curvature, we are measuring the distances from here to here, opposite to the direction of light ray. Opposite to the light ray direction is in this one, and we are measuring the distances in this one. Here the sign convention will be minus negative for these distances. In this way we can write, suppose f is the distance, fp is the focal length, right? Focal length is fp. Okay, so we put a negative sign between my before minus, that means this is measured opposite to the light direction. Okay, and same radius of curvature cp, suppose radius of curvature is cp. Here we also put some negative sign before cp, that is radius of curvature. And in this way the sign convention is put like this. So if you measure, if it is a convex mirror, if it is a convex mirror, is a this is concave, just I am writing besides this mirror a convex mirror, this is incidenting on it and it will be reflecting back. So if it is the pole of the convex mirror, we can write the principal axis, this is moving through focus. Okay, not a straight line. Okay, this is passing through focus. Okay, so this is actually a real ray reflecting back, and this is not, this is exactly not the real ray, and we will be extending this ray, we can denote with some dotted line. Okay, so this is the focal length. So if we consider a convex mirror, see here the focal length will be measured from pole in the direction of the light. What is the direction of light? In this direction. And the focal length is also measured in the same direction. So for a convex mirror, the focal length is can be written as PF, and there is no negative sign here. Okay, we can consider it as positive. In this way, so the sign convention plus or minus we have to give the to the values measured from the pole of the mirror. And there is another rule here. If this is the principal axis, and whenever we consider the distance above the principal axis, that means if you put an object here, AB, this object, the height of, if you consider this object height as h, that object height is considered as positive because this is above the principal axis. And whenever there is some image is formed, that inverted image, and this is below the principal axis, this is inverted image, the distance, the height of the image is suppose h dash, this is below the principal axis. The distances measured below the principal axis are considered as negative. Okay, AB is equal to H is positive. So here B dash A dash A dash B dash is considered as H dash as negative. So this is the sign convention for distances measured from the pole and the distances measured above the principal axis and below the principal axis. This is sign convention. We should understand this sign convention very carefully before going to derive the formulas. Okay. So next, what is focal length of the spherical mirror? We see what is the focal length of a spherical mirror. Focal length, that is denoted by F. Focal length denoted by F. So here, what is the focus? Focus means it is a point where all the incident ray coming parallel to the principal axis. We will see what is focus for a concave mirror. Whenever there are incident light rays parallel to the principal axis, coming parallel to the principal axis, all these rays will be coming and reflecting back, passing through a fixed point. Okay, whenever there is a light ray incidenting parallel to the principal axis, it will be reflecting back and it will be passing through a fixed point F called focus of the spherical mirror, and this length is called focal length. The distance from the pole is called focal length. See, in case of a spherical mirrors, the center of, see the point, the line starting from center of curvature to the this point, this is called a pole. Okay, and if it is a spherical lens, we see that lens, what is lens in the next classes. That is, here the point of a spherical lens is called optical center. In case of a mirror, it is called pole. In case of a lens, it is called optical center. So these two terms you should remember. What is a pole? What is an optical center? Whenever it is called pole, in which case it is called optical center. So here the focus, we are now want to derive the formula for focus. Okay, This is, suppose we consider as center of curvature. So a point where all the incident ray incidenting parallel to the principal axis, where all the reflected rays will be coincide, is called the focus. Okay. So here, if we consider a ray coming out of through center of curvature and touching this point, the ray will be exactly reflected back, because at this point of incidence, as we already seen, the light ray incidenting normal to the surface. Okay, so this is the definition of focus. And in case of a convex mirror, see how will be the focus, we will see with diagram. If this is the principal axis and some light rays are coming and incidenting on a convex mirror, okay, this is the principal axis, this is pole, this will be they will be reflected back like this. Okay, so all these rays are actually, if you extend these rays, actually they will appear to meet at a point. Okay, they actually appear to meet at a point. These are not real rays, called virtual rays. And see, the point of divergence in case of a convex mirror, it is called, focus is called point of divergence. In case of a concave mirror, it is focus is called a point of convergence, because all the rays will converge at a point. Here, from the focus of a convex mirror, all the light rays appear to diverge from this point. That is the difference. This is focal length as usual, from pole to focus. So this is the definition of focus in case of convex and concave mirrors. See, all the rays coming parallel to the principal axis, all the rays coming parallel to the principal axis are not exactly parallel with the principal axis. If you consider in practical, so there will be some, they will make some small angles with the principal axis. So this is called a paraxial approximation. So there are no perfectly parallel rays with principal axis. Okay, so here there is some point called focus, we already discussed, where all the rays will be reflecting back and passing through this point called focus. And these incident rays, reflecting rays, and the point of focus all lie in a plane, on a single plane, all lie in a plane where this plane is passing through the focus. This plane is passing through the focus. So this plane where all the incident and reflecting rays are passing through is called a focal plane. So here we need to remember two things here: focus and what is focal plane. Okay, so now we see what is the formula for focus. This is the principal axis, this is a spherical mirror, and this is center of curvature, this is focus. Okay, if you draw a line, this instant point, and if you draw a line from here, this instant point. Okay, so here if you see, This is center of curvature, this is pole, this is point M. And if you draw a perpendicular to this from point P to M to P, okay, we draw a perpendicular from here to point P, this is 90 degrees. Okay, so here if you see that an object coming, if you put an object here, the light rays will be incidenting on a spherical mirror. So if you consider this as theta and the light ray is coming from an object parallelly to the principal axis. So what is the incident angle here? What is the incident angle? Incident angle is, this is the incident ray of light. This is the line passing through center of curvature to the incident point. Here the angle between the radius of curvature to the incident ray is called angle of incidence. Okay, and by the principle of reflection, if it is the angle of incidence, this is also angle of incidence theta. This is theta and this is also theta. See, with the diagrammatical symmetry, if you observe theta plus theta, this is 2 theta and this is also 2 theta by the diagrammatical symmetry. And if you observe, this light ray is incidenting and exactly coming, passing through the focus. Okay, so here see, what is the focal length here? This one, and this distance is the radius of curvature from center of curvature to the pole. So we see what is the formula for focal length. You observe the diagram MCP. MCP. So if you observe this diagram, we can write tan theta is equal to, what is tan theta? See, this can be considered as a perpendicular to the principal axis. So MP by CP, opposite side by adjacent side. MP by CP. If you observe this triangle MFP, we can write tan 2 theta is equal to opposite side by adjacent side by the property of triangle MP by FP, right? Tan 2 theta is equal to opposite side by adjacent side MP by FP. So here if you see, if the for a small angles of theta, we can write the first equation, this is the second equation. We can write the first equation as theta is equal to MP by CP. And the second equation, if the angle of incidence is so small, we can write the second equation as 2 theta is equal to MP by FP. Okay, MP by FP. So what is theta here? Theta. In place of theta, you put here MP by CP is equal to MP by FP. Okay, MP gets cancelled. Okay, and if we can rewrite this equation as 2 FP is equal to CP, right? Can rewrite MP will be cancelled. We can rewrite this equation as 2 FP is equal to CP. If you observe, what is FP? Here FP is focal length, right? 2 into F is, what is CP? Here radius of curvature, that is R. That means this equation we can write from this equation we f is equal to r by 2. Focal length of a spherical mirror is half the radius of curvature. Okay. So in this way we can derive the focal length of a spherical mirror. Next, we will derive what is a mirror formula. What is a mirror formula? So these are the important topics in the ray optics and the fundamentals you need to understand before going to the problems, and we will apply these fundamentals to the optical instruments that we are going into the next classes. So here the mirror formula. For the mirror formula, to derive the mirror formula, we need to understand the sign convention which we have already discussed. And if there is an object put in front of a spherical mirror, okay, the light rays will be coming out of this spherical, coming out of this object. The light rays coming from the object if AB. Okay, AB is the object, and this is the object, and this is the center of curvature. Suppose this is the center of curvature, this is the focus. Okay, these light rays from the object will be coming and falling on the spherical mirror. So there are actually four considerations how the light rays will be considered for calculation purposes. See, the four kind of rays: the ray which is incidenting parallel to the principal axis, okay, and the ray which is passing through the center of curvature and incidenting at the spherical surface, this is center of curvature, this is focus, okay, and ray incidenting on the pole of the spherical mirror. So these three rays will be reflecting back. If you observe this light ray, this will be reflecting back through focus and meets this here. And if you observe with the help of laws of reflection, this will be reflecting back, and this will be, these all three rays will be meeting at some point between center of curvature and focus, B dash A dash. Okay, so in the here we consider it as B A. Okay, B dash A dash A B, and this is the pole, and M N is the spherical mirror. If you consider M N is the spherical mirror. So here four rays generally we consider when we want to create an image out of an object put in front of the spherical mirror. These three rays we know are incidenting on the spherical mirror, and the fourth one is if a light ray is passing through the principal axis and touching the pole, the light ray will be coming back, reflecting back exactly, and retraces the same path along the principal axis. So according to the principle of laws of reflections, these rays will be reflecting like this. The coming, passing through the center of curvature will be exactly reflected back, and will be passing back to the through center of curvature. So here, if you observe the diagram, this B dash A dash F and triangle MFP. If you observe this diagram, the triangle B dash A dash F and the triangle MFP are similar triangles by the diagramical symmetry. So here, if you want to know these diagramical symmetry, and you can draw a line from M to P, the perpendicular, you can consider it as a perpendicular with the principal axis. Okay, a line drawn from M to P. So this line will be perpendicular to principal axis. We ignore the curvature of spherical mirror, and we can consider this as a perpendicular because the variation of distance here from pole to this line will be so small when compared to the length of the perpendicular. That's why we can consider this as a perpendicular to the principal axis. So here, if you observe these two triangles, see, from triangle B dash A dash F and triangle B dash triangle B dash F A dash and triangle M F P. Okay. Here, if you observe, we can write B dash by A dash is equal to B dash by A dash is equal to B dash by A dash by MP. B dash by A dash by MP is equal to B dash F by FP. B dash F by FP. This is equation 1. B dash by A dash by MP is equal to B dash F by FP. We can write this equation with the help of symmetry of triangles. Okay, and see here MP. What is MP? The height of the object. See, if you observe this two, MP is equal to AB, and this one we can write equation 1 as B dash by A dash is equal by MP, that means AB is equal to B dash F by FP. Okay, so in the next second case, if you observe the two triangles APB and B dash P A dash, if you observe the triangles APB, B dash P A dash, these two triangles are also similar triangles. See, from triangles APB, triangle B dash P A dash, B dash P A dash, so triangle B dash P, we can write, see, B dash by A dash by AB, we can write B dash A dash by BA or AB is equal to B dash P by BP, B dash P by BP. Okay, observe this one, B dash by B dash A dash by BA with the symmetry of the triangles. These two triangles, triangle APB and triangle B dash FP A dash, these two triangles are similar triangles. Okay, so with By these two triangles we can write this one b dash a dash by ba, b dash p by bp. If you take this as equation 2, okay, see if you observe this one, b dash a dash by ab, b dash a dash by ab or ba, whatever you can write, so is equal to b dash f by fp. So with these two equations we can write, see we can write b dash f by fp is equal to b dash f by fp is equal to b dash p by bp, right? See, b dash f by fp is equal to this b dash f is equal to b dash a dash by ab. So here what I have written, this I have written equal to this one. So I have equated this one and this one. So this implies b dash f. What is b dash f? Observe this one, b dash f. We can write b dash p minus fp. See this length b dash f, this one b dash f can be written as b dash p minus fp, right? B dash p minus fp by fp is equal to b dash p by bp. This b dash f I have written b dash f is equal to b dash p minus fp gives b dash f. So I have written this one. So here if you observe this equation, these are actually the lengths. Suppose the focal length, radius of curvature, b dash f p fp, b dash p bp, these represent some lengths in this diagram. So what we see, what are those lengths? Okay, we see what are those lengths. See b dash p. What is b dash p? Observe b dash p. Observe that one. Here this is the image b dash p. So this is the image distance, right? b dash p is the b dash p is image distance. V, image distance is v, object distance is represented with u. Fp, what is fp? Focal length. So fp is focal length, right? What is b dash p? We have written bp. bp. So if you observe this as object, bp is the object distance, right? bp is object distance u. Here in ray optics, u is object distance is represented with u and image distance is represented with v. See, according to sign convention, if you observe VFU, all are negative because all are distance measured from P only and opposite to the incident ray, light direction. So if you substitute these values in this equation, suppose it is considered as 3, substitute these values in the equation, the equation becomes b dash p minus of minus f by fp minus f by b dash p minus v by bp minus u. Okay, just I have substituted these values in equation 3. Okay, so this will become minus v plus f by minus f is equal to v by u, right? Okay, if you rearrange this equation, we will get 1 by u plus 1 by v is equal to 1 by f. 1 by u plus 1 by v is equal to 1 by, if you rearrange these terms, you will get this equation, and this is the very important mirror formula. Okay, so u is the object distance bp, v is the image distance b dash p, f is the focal length, this is the focal length. So this is the mirror formula, and we will use this formula for the problems we will do when we are going to do some problems in the next classes. So this is how the mirror formula is derived with the help of a diagrammatical ray diagram representation. Okay, so observe the steps once again carefully. So this equation I have written in this form, and this can be rearranged. So if it becomes f minus v, and if you take 1 by f into one side, and the equation can be rearranged in this form. Okay, so this is about the topics and introduction about ray optics. In the next classes we will see what is refraction and what is a lens formula, and we will do some problems which will be appearing in neet and JEE exams. Okay, thank you.